So we're going to go shallower, and we're going to focus on intermediate depth earthquakes now. And here we have the same sort of issue that we have for deep earthquakes. The mechanism is not necessarily well constrained yet. So what I'm going to try and provide today is some seismological observations that should help us constrain this mechanism. I don't have the answer yet, though. So I'm just showing you here a map of the seismicity around the world, and of course, we're going to focus mostly on the green dots, intermediate depth earthquakes. And here I'm just noting that most of them occur along subduction zones. Our next talk will talk about some of them that are not along subduction zones, just to remind you what's going to happen next. And I'm going fast here because most of this we've already seen in the previous talks. So we separate deep earthquakes between intermediate depth earthquakes down to about 300 kilometers, and then from, let's say, 400, 450 to almost 700, we call them deep earthquakes. And the separation is mostly due to this sort of behavior of the seismicity. What I'm going to try and do is focusing on this region here, on the intermediate depth earthquakes, to look into the behavior of the seismicity, how many events we have, large versus small events, aftershock sequences, things that we've already seen in the previous talks, but focusing on the intermediate depth earthquakes. And as I said, the mechanism responsible for this type of events is not entirely clear. The temperatures and high pressures that we expect below 50 kilometers depth would suggest that the rheology of the material of the subducting plate would not be brittle. And then the question is why we still have 25% of the seismicity, of the global seismicity along the subduction zones. Is the composition to blame? Is phase transitions or metamorphic reactions, dehydration reactions to blame? Is something controlled by temperature, water content? This is the main question, or one of the open questions in seismology about the mechanism of these two intermediate depth earthquakes and deep earthquakes as well. But I'm going to focus on the IDEs for now. And this is a textbook type of plot showing the subduction zones, the seismicity along subduction zones in the East Pacific. And what you see is that for all these cross sections, we have seismicity going all the way down to 670 or so kilometers. The seismicity aligns with mostly the top of the slab, including the crust and the upper mantle of the subducting slab. And you see that they all seem to share that behavior. Maybe the complexity or the geometric complexity varies along between these subduction zones, but they're mostly following the top of the slab that's subducting. This is called the Varati-Benioff zones. This is what we usually use to design slab 2.0 now, is to follow the seismicity and assume this is related to the top of the slab that's subducting, which is fine. But the interesting part about these Varati-Benioff zones, when you zoom in, is that they're a little bit more complex for intermediate depth earthquakes. So we don't have the olivine wedge, the metastable olivine wedge, but we have this really interesting structure that people have seen since the 70s. This is in Honshu, where you see seismicity along two layers. One upper layer that's mostly in the crust of the subducting plate, and one lower layer that is mostly in the mantle of the subducting plate. And in between, you don't have any earthquakes, or not many earthquakes. So you have a seismic region separating the two layers. This is called a double Varati-Benioff zone, or double seismic zones for short. And of course, whatever the mechanism responsible for intermediate depth earthquakes is, needs to be able to explain this sort of behavior. So this is an example in Honshu, but again, since the 70s, it's been clear that this sort of double seismic zones, or sometimes triple seismic zones, have been observed in different places. But most of the observations had been on individual local or regional networks, until this paper by Brodzinski and co-workers, where they use the relocated catalogs, global catalogs, to study whether these double seismic zones are a global feature. And what they conclude is that it is, in fact, something that happens in most, if not all, subduction zones. And what is also interesting is that when you look at the separation between the upper layer and the lower layer, let's call it the thickness of the double seismic zone, it varies as a function of the age of the plate that's subducting. So here is this here is showing the histogram of the density of seismic events in the upper layer and in the lower layer, and the x-axis represents the age of the plate. So younger plates have double seismic zones that are pretty thin, like in Chile, for example, and I'll show you a few examples. And over here, you have very thick double seismic zones separated by almost 40 kilometers. So people seeing this very clear pattern, people have studied what can explain the double seismic zones. And if you look at dehydration embeddlement, one of the mechanisms that is favored for explaining intermediate depth earthquakes, it is consistent with the location of the seismicity along double seismic zones. So this is a classic plot now by Hacker and others, where you can predict the presence of hydrated minerals along the subducting plate, and it sort of agrees with the location of the double seismic zone. So in the middle, you don't see any dehydration reactions yet, so you have no seismicity or very little seismicity, and on the top you have hydrated minerals, and at the bottom you have hydrated minerals, and then when they dehydrate because of increasing temperature or pressure or both, then you can have intermediate depth earthquakes occurring. Now, so I want to focus on that because we're going to look at this very carefully at the global scale, but I also want to show you and bring your attention to the fact that at some point, these dehydration reactions will stop. There's no more hydrated minerals, and at some point they should close. So the double seismic zone should close at some point. And with the networks that we have available today, we are now able to define when this happens. Or that's what I'm going to try and convince you of. Of course, there is discussion about this, because if you look at the picture over here, on the top of the slab, it's clear that, during the history of the subducting of the plate that's eventually going to subduct, there's water coming in due to faults and whatnot on the top of the slab. But you also have to explain how you can bring water all the way down to 40 kilometers within the slab. So that's not necessarily an easy task. And there's, again, a lot of discussion of how this happens. How can you bring water down 40 kilometers within the slab so that you can hydrate the lithospheric mantle that's going to eventually subduct, and then dehydrate it when you get down to 100 kilometers or so. So I'm not going to explain these two plots or anything like that. I'm just showing you that there's still discussions about how you can really hydrate the lithospheric mantle. And if that's possible, then you can argue that you have hydrated minerals in the right place at the right time. So what I'm going to try and show you today is looking at the global scale. We want to characterize double seismic zones. That is, characterize the width of that double seismic zone and characterize when it ends, when you eventually don't have any more seismicity due to this hydrated mineral, the presence of hydrated minerals. And the second part will be about the seismicity behavior. So we've seen a few talks already where we look at V-values, how V-values change for deep earthquakes. We talked about aftershock productivity or aftershock behavior in different regions and how, you know, the detection limits might look like there's no aftershocks, but when you look carefully, you may have some aftershocks. So I'm going to talk about this for the intermediate depth region, intermediate depth earthquakes. And before I start, I want to show you how we relocate the catalog. So originally, the catalog is based on P, S-peaks, and maybe some depth phases that an analyst is able to detect and pick. But to really constrain the depth of an event, it is quite difficult. But there's something called depth phases, and this is an example of a depth phase. It's a little pp. The little p part goes up, bounces off the top of the Earth, and then goes back down, goes into the mantle, and reaches the station at 40 degrees in this example. And there's obviously the direct P wave that's going all the way through the mantle. Because the path of little pp and p is similar, not exactly the same, these distances, then you can, the difference between the arrival times of p and little pp are correlated with the depth of the event. So this is a simple model where for 140 kilometers depth, the difference, and 150 kilometers depth, the difference between little pp and p are 30 seconds or so. But particularly, the difference between these two, even though the depth is only 10 kilometers, the difference between the little pp times is very robustly correlated. And it's less dependent on the distance of the stations and the source. So we do this by using, and again, we've seen this before, so we use a vespergram here, and we develop a code to first design or take an array of stations of about 1 degree in aperture, and for each event we can get the p time, the little pp, and sometimes little sp. We don't use little sp for now, but we could, and we can estimate automatically pick the p and little pp arrival times. So we have the difference of the two. And this is an example of two events in Chile at 117 and 111 kilometers depth, and the peaks of little pp minus p at different arrays along North America. So these are permanent or almost permanent arrays, and you can see that they don't fit exactly in the line, but they're pretty close. But what's even more interesting is that you see for each array there seems to be sort of a station term, a static term that's associated with that particular array. So most of these 4 stations are always above the line, and these stations here are always below. So there's some sort of station term. So we use a double difference, little pp minus p arrival time, to relocate the events. And when we do that, then we get something that looks like this. Now, at the global scales, we can really see at each of the subduction zones that I'm showing here, but we have as much as 32 slab segments. On all of them, we can see double seismic zones. And on most of them, we can visually see which one is up and which one is low of the double seismic zone. We can get the thickness, and in some cases, we can even see when it closes down. So we're going to use this new sort of relocated catalog for the following work. So here are 4 examples of double seismic zones in different places. And the other thing that we do is usually you would estimate the thickness of the double seismic zone. But the thickness doesn't make really sense because at some point the double seismic zone is supposed to close down. So where do you measure the thickness is kind of an open question. So what we do is we do a double spline fit with a black curve and a red curve to select all the events that belong to the upper seismic zone or upper seismic layer and the events that belong to the lower seismic layer. Of course, in some cases, there are some events that are undefined. We acknowledge that, of course. But in some cases, it's very clear where each of these events belong to. Now, for the thickness, we estimate starting here to the right or starting here to the right again. That's where we estimate the thickness of the double seismic zone based on the spline fitting curves, not on the data. And we can also define the depth of the closure of the double seismic zone. That's obviously an extrapolation in many cases, but it's pretty clear in some cases where it happens. And we do some bootstrap to estimate our uncertainties on those parameters. So we have thickness of the double seismic zone and width of the double seismic zone. So when we plot that, the green dots are going to be the paper by Budzinski in 2007, and this is our data now. So again, similar to what they concluded, the thickness of the double seismic zone is strongly correlated with the age of the plate that's subducting. So we have thicker double seismic zones for older, usually colder subducting plates, but ours are a little bit thicker than what Budzinski estimated. And I think that has to do with a couple of things, but one is that our measurement of the thickness is based not on some Gaussian fitting, but actually using these spline functions. And I think they're more robust in that sense. That's me, sorry. The other observable that we have here is the maximum depth or the closure of the double seismic zone. And what you see is that this one is more correlated or strongly correlated with thermal parameters. So somehow the maximum thickness of the, the maximum depth of the double seismic zone is controlled by the thermal parameters. So maybe, or not maybe, it's probably thermally controlled, and that's the point where all dehydration reactions would eventually stop, if you believe that dehydration is the mechanism that explains intermediate depth earthquakes. But this is probably the first time that this has been done at the global scale. So I think it's interesting to point that out. Okay, now let's go even further into the seismicity. So as I said before, we can separate upper layer and lower layer of the double seismic zone. So we're going to study them independently. And one thing we're going to do is look at the v-value, as Sean showed in some examples. We want to look at the v-value, and here are some reasons why. So the v-value is basically showing the relative number of small events compared to the relative number of large events in a particular region. And in many cases, people have seen that it correlates with differential stress, negatively correlates with differential stress. In some subduction zones where you have lots of local regional data, people have done this, and I'm going to show you a few examples of v-value maps along subduction zones. So these are maps, v-value maps from 0.7 to 1.5. The typical number we usually use is 1. And you have anomalies, red anomalies here of very large or larger v-values that people interpret as being related to dehydration reactions, or at least the presence of free water in the system. Here's another example. This is in both Alaska and New Zealand. This is one of the earlier papers that had done this. What I want to point out here is, again, there's these regions here with anomalous v-values, higher v-values. And the other thing that I want to mention, or that's the way I interpret it, is that these anomalous values, anomalous red zones, are mostly in the upper part of the subducting plate. That's where the dehydration reactions are more likely, of course, and maybe more water is present. And that's where maybe this water is coming out and eventually goes up to feed the volcanic systems. But if you look at the bottom part of the subducting plates, of the subduction zone, the V values there are usually blue, so lower in some sense. But again, this is based on local data. It's not a global characterization. And here's just another example of that. So what we did is we used our separated upper and lower seismic zone catalog, and we estimate V values in all the 32 segments that I showed you before. And what you see, here's just two examples of the fitting procedure. What you see in the end is that the V value of the upper layer is always higher, and it's always higher. It doesn't really, the absolute value is not necessarily very robust, but it's always higher than the same, the V value of the lower layer in the same subduction zone. So that's one important thing. It's always higher, so it's red, and this one would be bluish. The other observable is that the V value is dependent on the age of the plate that's subducting for the upper layer, while it's more or less constant for the lower layer. So somehow the V value here is controlled by age or temperature, while here it's sort of independent of what the plate age of the subducting plate is for the lower seismic layer. So if we believe the interpretation that we had on the previous slides for individual subduction zones, our results are consistent with dehydration in the upper layer of the double seismic zone, but points towards a relatively dry lithospheric mantle in the subduction zone. So that's sort of the main conclusion so far. Now, what I want to do next is to look at aftershock sequences. So intermediate depth earthquakes and deep earthquakes tend to have a small number of aftershocks in general. If you use template matching, for example, you can increase the numbers, but they're usually very small in magnitude anyway. So for an 8, you would expect a few 7s and a few 6s aftershocks, but they don't tend to happen that often. So what I'm going to do is I'm going to take this catalog here. This is northern Chile. And I'm going to take all these events that are magnitude 5.5 and above, and all these events 5.5 and above for the lower layer. And I'm going to use this catalog here. This is developed by Sippel, a recent paper in northern Chile, where you can clearly see the double seismic zone. So I'm going to take this as the main shocks, and I'm going to find aftershocks in the catalog in the picture above, and see what we get. Do we have aftershock sequences? That's first. And second, are they any different between upper and lower layer? So here are two examples. This is an earthquake on the lower layer, a magnitude 6.5, 120 kilometers depth. We found 13 aftershocks after 5 days of the event, and these are located here. So this is the main shock, just a big circle because just to show it to you. It doesn't have anything to do with its size. And then all these blue dots represent what I call aftershocks. So they are within 0.5 degrees of the main shock. And this is the temporal behavior of the aftershocks as a function of time after the event. And you can see a slight slope here, typical of an aftershock sequence. The plot here is the same for an event in the upper layer that we defined as an upper layer event. And you can see a much richer aftershock sequence with a much richer temporal behavior that lasted maybe a day or so. So still small number of events, but a significant difference between the two. Now, as Cliff would explain in one of his many papers on deep earthquakes, because there are not that many aftershocks, you can align all your main shocks as time 0 and then stack the events as a function of time. So I did that. So this is just a zoom-in version of the plot before. I did that, and what you get is sort of a complicated figure here. Each one of these dots represents a single event and its aftershock sequence for the upper layer and the lower layer. But this is sort of the stack version of that. So you see for the upper seismic layer, you can see a very nice aftershock sequence, while for the lower layer, it's not as robust, there's still a slight aftershock sequence, but it's less productive. So when you look at the productivity of each of the events, once you account for the effect of the magnitude, the fact that a large magnitude event will have more aftershocks, once you correct for that with this sort of relationship here, you can see that the upper seismic layer is 3 to 5 times more productive in terms of aftershocks than the lower seismic layer. And that, to me, points again to differences in the behavior and potentially differences in the mechanisms that explains intermediate depth earthquakes for the upper layer and the lower layer. So what I'm pointing out here is those differences are robust in terms of seismicity, so maybe the mechanisms ought to be different too. This is just an example. We also have data from Japan. This is just an example of one particular event and its aftershock sequence, and another event in the lower layer and its aftershock sequence. So I think this is a robust observation. We're going worldwide to try and define it. So I'm going to stop here. Maybe you can ask questions. But there's other parameters that we ought to look into once we have the upper and lower layers separated. Are the stress drops different? Are source time functions any different? Is radiated energy efficiency, things that Sean Wen talked about, any different? And maybe with all this together, whatever the mechanism we want to find to explain these events needs to be able to explain the difference between these double seismic zones and the differences within each double seismic zone. Thank you very much.